So in the last video, I really spent a lot of attention explaining the theory. If you're fine with that, you can just immediately skip to this video because here is where we start making the exercises. So for this, let's move to question number 1, where we have to determine basically the sine, cosine, tangent value of a certain angles. So for this, let's start up with a warm-up and let's have a look at our first question A. So here we are asked to find the sine value of 0 radians or 0 degrees. In that case, it doesn't make any difference. So there are two ways in which we could calculate this, right? The first way we could do it is by just looking at our table and seeing over here, okay, 0 degrees, sine value, so this one and this one, let's have a look at those. Okay, we get a value of 0. Okay, we can already immediately write that down and be totally satisfied. But what I do want to stress is there is another way to doing it. Basically, by just using this unit circle, you didn't actually need this table, especially for values like 0, pi over 2, pi, and 3 pi over 2. These are actually very easy to know, because here at 0, it means that we're still here at base, basically. We haven't moved. We haven't done, or our angle line hasn't gone up anything. So we're stuck in this coordinate over there, right? Because that's where it intersects with our unit circle. Meaning that our x-coordinate is going to be 1, so our cosine value will be 1, but our sine value, which keeps track of our y-coordinate, is just going to be 0. So we can also just write 0 in that way. Okay. Then let's have a look at another one. And here I'm going to show you two ways to do it. You don't have to do it that way, but it's just nice to know a couple of ways of doing things. So tangents pi over 4. For this, what you could just do, you could say, well, tangents pi over 4, 45 degrees, it's 1. Okay, and you would definitely be right. Nothing more about it. But actually what I want to stress is that knowing these sine and cosine values is enough. Because tangents and cotangents, these are just combinations of these sines and cosines. Because remember, tangents is just our sine value divided by our cosine value, and our cotangents would just be our cosine value divided by our sine value. Meaning that you could just rewrite it if you say, oh, I really don't remember what was up with these tangents. The only thing you have to remember is that tangents is sinus over cosinus. So sinus pi over 4 and cosinus pi over 4. And in that case, well, if you only remember the two first lines, you could say, oh, those are both square root of 2 over 2. So it would be square root 2 over 2 over square root 2 over 2. Which of course ends up being 1 again. You don't have to solve it that way, just to show you that if you have these tangents over here, the cotangents, and you don't know how to calculate it back, you can just use the first two lines of your table. Okay, now let's move on to something that's a little bit more challenging than just reading it off immediately from the table. And we are looking for cosine of 5 pi over 4. And I can hear you thinking, but 5 pi over 4, that wasn't given. It's not in our table. And no, it's not given in our table. And this is basically what I've been talking about, that you need to be able to convert angles back to this quadrant. So for that, let's first determine where it's going to be. So in that case, well, we always try to find some kind of anchor points to be able to draw it. So, or you can just know the angles by heart. You say, oh, I immediately know that that's going to be 225 degrees. That's also fine. But one way of considering it is going to be cosine of pi plus pi over 4. And I think this is a very powerful notation. Because what does this teach you? Well, it teaches you that you traveled pi, or 180 degrees, to pi radians. But you didn't stop there. You went a little bit further, and you went another 45 degrees, and you went. So another pi over 4, and you went all the way over here. So basically, if we use this red line to keep track of how our angles goes, we go counterclockwise, it means that we end up over here. Okay, so that's already interesting, because we can see, okay, this pi and pi over 4, well, it's just going to be the same as traveling 5 pi over 4. But not only that is, now we want to convert this back to this quadrant over here. And how are we going to do that? Well, for this I want to draw your attention to the cosine and sine and really try to remember what it does. So for cosines, we're interested in our distance on our x-axis. So how would we read our x-coordinates over here? Well, we would look at this intercept, right? We would look at this point over here and we would say, oh, our cosine value is going to be more or less over there. Okay, and now you must think, is it possible to draw, well, an angle, well, a triangle over here that's going to look much the same as this, but for which we do know the table? In that case, well, yes, it's possible. You could say, well, what if we extend this over here? So this is going to be now pi over 4 away from our base case scenario where we have traveled 0 degrees, so just 45 degrees. And I know it isn't really 45 degrees, it will be more like 30 degrees, but it's mainly for visual thing. So in this case, yeah, okay, you say more or less over here. And what's interesting about this now is if we look at this x-intercept, is that it's going to be the same distance as this one over here, but just on the positive side of your origin, and this is going to be on the negative side of your origin. Meaning that this distance, let's call it whatever, let's call it, I'll call it gamma, is going to be the same as this distance over here, but with a negative sign in front of it, so negative gamma. Meaning that we can just look up our cosine value for pi over 4, right? So pi over 4, let's look in our table, it's square root 2 over 2, meaning that we haven't traveled square root 2 over 2, but we are at minus square root over 2 over 2, right? And many of you might have learned, got taught relationships like this in high school, that it says the cosine of some angle alpha is going to be equal to the negative cosine of that same angle plus 180 degrees or plus pi. And this is actually where it comes from, because you see, we only traveled pi further away than our original angle, well, our angle pi over 4. So I'm not a big fan of you learning these things by heart, because, well, it's not necessary to learn them by heart if you just understand how this circle works. If you know that, well, the trick is always to try and find an angle over here that we can easily read off, and that's going to be the same distance for either our x or our y axis, maybe with a negative sign in front of it or not, that's enough. Okay, that being said, let me clean this up because we're going to make some more exercises and otherwise it's going to look super messy. So let's clean this up a little bit. I think I already wrote enough angles over here. Okay, and then we're going to move on to question number 8, where we're interested in finding the negative 7 pi, the sine of negative 7 pi over 6. So question H, sinus of minus 7 pi over 6. 6, not 0. Okay, so in the previous video I shortly talked about, well, angles and saying that, well, we all agreed that we're going to go counterclockwise. Well, there is a way of going clockwise. Basically, you take the negative angle, right? It means you start over here, and instead of going that way, you go, okay, minus pi over 2, minus pi, minus 3 pi over 2, minus 2 pi, right? So that would be the opposite way around. So in this case, let's try and draw this. So what we know is that we didn't only travel back pi, because we could rewrite it as minus 6 pi over 6 minus pi over 6, or let me rewrite it a little bit easier, and we can already say that, or minus pi over 6. So we didn't only travel minus pi, we traveled another minus pi over 6. And for this, let's draw it. So we went from here, traveled all the way over here, minus pi, and then we traveled a little bit further, and we traveled another pi over 6, another 30 degrees. So we end up more or less over here. It's not perfectly drawn, but, well, just bear with me. It should be, I think, a little bit lower. Well, I can actually just correct it now. It should be more or less like this. This looks more about right. Okay. And now we're interested in our sine value. And for our sine value, remember, we're always interested in finding our coordinate on our y-axis. And for this, well, how would you read your y-axis coordinate? We would just look over here on your axis and say, well, it's going to be this height. So we just draw a line perpendicular to the y-axis. And now you're like, okay, we're over here, but how can we understand this angle? Well, all you want to do is find this point over here. And we can read that point over here by finding another angle that we do know stuff about. Well, the angle we do know stuff about that's going to intersect at exactly the same point is going to be pi over 6, right? Because that will move it up as much on both sides, because this moves it up pi over 6, and this will also move it up pi over 6. Imagine that you would start over there, right? So in this case, well, we just need to read our sine value of pi over 6. And our sine value of pi over 6 is going to be 1 over 2. So our sine value of minus 7 pi over 6 is also going to be 1 over 2. Okay, then one more of these. I'll make question I with you, and then I'm going to recommend at home that if what I'm doing here seems really strange and you have no idea what I'm doing and it's really unclear, try to make all of them, right? Because these are really elementary things under understanding this unit circle. And if we ever get back to complex numbers, you will need to understand this too. You will need to be able to work with this very, very fluidly. Okay, so for this and then we're interested in finding cosine of minus 37 pi over 2. Okay, and this is interesting because in the previous video I shortly explained that, well, when we are going around this circle, if you move 2 pi around, you basically end up just over here. You end back up at your starting position. If you do 4 pi, you end up at your starting position as well. So when you get these really large numbers with pi in it, try to always isolate 2 pi out of it. So I'll let you think about it, how many times you can isolate 2 pi out of this. And then you will still have some movement at the end. So basically what you're trying to do is get out how many times we just walked around the complete circle, because that's not going to give us any extra information. And in this case, well, you could say that this is the cosine of walking around the circle 9 times clockwise, and then going a little bit further, going another minus pi over 2. You will see, if you will just add these up together, you get indeed minus 37 pi over 2. So why did I isolate this? Because, well, it basically means that we go around the circle clockwise, not counterclockwise this time, because it's a negative. 1, 2, 3, 4, so on, and all the way until we have gone around exactly 9 times. And then we're going to move another pi over 2. So we're here at the base case scenario because we just went around 9 times. And then we're going to travel another minus pi over 2, meaning that we're over here. Okay, so what are we interested in now? We're interested in our cosine value. Okay, so if we have an angle over here, and let me draw it, basically that means our angle indicator is going to be here. Okay, over here. Well, the intersection between the circle is going to be here, right, at 3 pi over 2. And for this, well, you can convert it back to basically saying, well, this is going to be the same as finding a cosine in this quadrant over here as the cosine of pi over 2, because, well, it will indeed be the same movement along the y-axis. But we can already know it, and it's much easier because we can just immediately read where we are. And we are just on our y-axis, and we are -1 down on our y-axis for x being in the origin, meaning that this is just going to be equal to 0. So really try to see how you could walk around this circle and really try to make sense of that yourself. Okay, that being said, let's move on to the next exercise. For this, I'm going to discuss the function with you, and I'm going to plot it a couple of times in Desmos so that it makes sense to you. And Desmos does a much better job of drawing things than I do, but it is important to, well, basically know what I'm doing and how to calculate these things. And sketching, well, I'll show you how to do it as well. So for this we move on to 2. And we're going to start easy, and we start with question A. So we're dealing with our first function, which is just our function is cosine of x. And that one I already plotted once. If my memory serves me right, basically we're dealing with this one over here. And this would just be our base case scenario. And I've already talked about it for a cosine. To walk around your circle completely, how many radians do we have to travel through? Well, we have to travel 2 pi radians, right? So we have to go completely around the circle. And in that case, well, the time it takes us to walk completely around this circle, which is 2 pi, it has a name, and it's called the period of your function. And the period of your function, in this case, is going to be 2 pi. But how do you know that? How can you calculate that? Well, there's a little formula you can remember. So you say a function, just a general function with a cosine beta b of x plus c plus d. So this is a very general notation. If we're interested in our period, the one thing that we're interested in is this b over here. This b over here will basically make you walk around the circle faster or slower. So, meaning if b goes up, it means you go around your circle much faster. If b goes lower than 1, it means you go slower around your circle. So, in that case, the trick for cosine and also for sine is going to be 2 pi over that b value over here. Of course, in this value, b is just 1, so it means 2 pi over 1. So your period is just equal to 2 pi. Okay, and then the other thing that I want you to find is the amplitude of your function. And for this, basically it means like how high does your function go? If we leave here at the origin 0, we can see our function tries up all the way to 1 and then all the way back to -1. How does it do it? Well, we're actually interested in knowing the radius of this circle, right? And for our standard sine or cosine, our radius of our function is always going to be 1. Meaning that we can never reach a value that's higher than 1 or more negative than -1. In this case, it means our amplitude. Our amplitude is going to be 1. So how do you know that? How can you calculate it? Well, we're actually interested in this value of a. So our amplitude is going to be equal to the a value, right? But here our a value is not given, and you could actually say it's equal to the absolute value of your a value, because a can be negative, and in that case, well, it's just gonna turn the function around, but it's not gonna change the amplitude. So how big is your circle, right? Okay, so that's for a. Then if you were to sketch it, well, you need to know where it's going to be equal to 0. It's going to be 0 for pi over 2 and 3 pi over 2, and then for every repetition after that, right? Okay, for now it's not that important, but how can you find it? Well, you would say 1 is cosine of x equal to 0. For this, well, now we'll talk about these inverse trigonometric functions, and you say, well, you get your cosinus, your inverse of cosines x, not x, 0 is equal to x. So your arc cosine, that's the name of it. So how would you find that? Well, you say, you look in your table, you look for 0, and you say, oh, that's going to happen at pi over 2. And then be careful, because it's not only going to happen at pi over 2, it's also going to happen at 3 pi over 2. It's going to happen at x is pi over 2 and 3 pi over 2. How did I find that 3 pi over 2? Well, you can know your geometric circle and say, okay, here cosine is going to be 0 and here cosine is going to be 0, because, well, that's why our x-coordinate is going to be equal to 0. And that's very true, you can do that. But also in the theory overview, I've given you a short summary of how you can keep track of those things. And then you basically say, well, just that much. So here you would say, okay, it's pi over 2, and here 3 pi over 2, or negative pi over 2, right? So it's this pi over 2 and traveling negative pi over 2 is the same as 3 pi over 2. So you could say it is either pi over 2 or negative and negative pi over 2, or you could even say 3 pi over 2. And this is a very special case because these are exactly pi away from each other, but what you're always going to say plus 2k pi, meaning that you will find a root again by walking around the circle completely again, and you'll again find that your cosine is, your cosine is going to be 0 there. And for this one as well. Okay, this one, you can look at it and you can already say, well, these things are just neatly going to alternate each other every pi, and this is a special scenario where you could just say pi over 2 plus k pi. So what do I want to stress out of this is this 2k pi is going to be your period. It's going to tell you how fast you walk around your circle, and here you see that it's, and here as well. So basically you need to travel all the way around it. And then k is an element of your integers, meaning that you can find an infinite amount of answers, but k needs to be -1, -2, 0, and so on, 1, a million. Basically, it depends on how many times you walked around your circle. For a million, I need 2 more zeros. Okay, then you can use that to plot it. You can say, okay, let's draw some kind of crude representation, and we're going to say, okay, cosine, when it's for our x is 0, what is that going to give us? Well, let's have a look. It's going to give us that it's 1. So it means we start up over here at 1, all the way then at x is pi over 2. Then we need to have 0. Then it's going to continue traveling until you have pi over here, where you're going to hit -1. And then it's going to continue traveling until you're at 3 pi over 2, where again it needs to be 0. So here it needs to be 0, and here it needs to be 0. And then you move on until you're at 2 pi, which is more or less over there, and there you're going to be 1 again. So if it's 0, we're going to be over here. Then when it's pi, we're going to be over here. At 3 pi over 2, we're going to be here, and at 2 pi, we're going to be here again, right? Meaning that we can sketch it more or less, and it's going to look like this. Of course, it's not a very good sketch, and of course it continues, and then here, well, you could also say, well, we could walk the other way, and you're going to find here at -pi over 2 pi, you're going to see a very similar pattern. So at -pi over 2, we're going to, can be at 0, at -pi, we're going to be at -1, and so on. So in this case, it will travel along like this. So you can already guess where it's going to cross the x-axis again. It's going to be at -3 pi over 2. Okay, that's as a very crude sketch. Let's have a look at Desmos. Basically here you can see the same pattern unfolding itself over and over and over again. So you can always draw them in Desmos to get a clearer overview of, well, what you're looking at. Okay, so that for A. Let's now move on to question number C. And for C, we're looking for tangents x. And in this case, well, we're interested in our period. And here I want to notice something interesting about our tangents. And for this, let's remove all of this here over here. So for our tangents, basically remember that our tangents is going to be our value of cosine over value over sine. So at this point where cosine and sine are equal, we're going to have a tangent's value of 1. But when you can cross it all the way over here, they're again going to be exactly the same again. They're just going to be now negative values, both cosine and sine, right? But minus over minus is just going to cancel each other out, so you end up with tangents is 1 again. Okay, and what if we're in these other quadrants? What if we're in quadrant 2 or 4? Well, in this case, sinus is going to be positive and cosine is going to be negative, but they're going to be the same. Well, they're going to be the same magnitude, but they're just going to be the opposite sign, meaning that your tangent's value is going to be a positive sine value divided by a negative cosine value, which is the same magnitude as a sine value, but with a different sign. So it's going to give you -1. And over here, just the same, but now your cosine is positive. Remember, we track over here, and your sine value is now going to be negative. So your tangent's value is going to be -1 as well. Meaning, so why do I draw this? It means that, well, every pi value, you end up at exactly the same value again, right? Because if you, in quadrant 2 and 4 or 1 and 3, you're going to end up with the same answer. So the tangent's value of, excuse me, not this, let's draw it like, the tangent's value of this point over here and this point over here is going to be the same, right? Or if we can draw it like this, it's also going to be the same, right? Because we're dealing with the same value of sine and cosine, with the same magnitude, but with an opposite sign. Okay, so why do I talk about this? Because before I gave you some kind of trick to determine your cosine, and I'm already going to tell you it's the same. It's going to be the same trick, so it's going to be 2 pi over b, also for sine, so sine bx plus c plus d. It's going to be exactly the same thing for sine. But for tangents, it's going to be fx is equal to, let's start over, so a tangents bx plus c plus d. This b is also going to make you walk around the circle much faster, and you're also going to use it to determine the period, but now the period is going to be not 2 pi over b, it's going to be pi over b. And this is not only for the tangents, it's the same for the cotangents. Okay, another thing important about our tangent functions is that our tangent function, I'll draw it shortly, does not have an amplitude. Okay, so for this, let's determine our period. Let's calculate it. So our b value is just 1, meaning that our period is pi. Amplitude it doesn't have an amplitude. Now let's draw it once. So basically over here, at these points, at pi over 2, you're going to end up with asymptotes. So at 0, it's going to be 0. Then it's going to be 1 at pi over 4. And then you're going to end up with some kind of asymptote. So let's draw that in decimals once and see what that does. So instead of cosine, we're going to have a look at our tangent value. And here you can see what happens, right? At this point over here, where your sine value is going to be equal to 0, right? You're going to hit this asymptote. And you're going to end up with these repeating patterns. So over here, the function goes to positive infinity, and over here, your function goes to negative infinity. And it keeps repeating over and over and over again. Here, it's going to be 0. Then here at pi is going to be 0. 2 pi is going to be 0, and so on, right? And you can also have a look over here at your 1 value. So really, it's going to keep repeating forever. And then maybe let's draw cotangents while we're there as well. You'll see it's much the same. It's just going to be the opposites, right? Okay. So that for our tangents, where we are interested in our period and our a. So if you have to draw it, well, how would you do it? You quickly draw some abscisse. You say, well, we know that every pi value, it's going to give us a problem, right? Because it's sine over cosine, we don't want cosine to be 0. So we can draw it. We can say, okay, here over 0, at pi, at 2 pi, we're going to get some kind of asymptote. I'll draw them in red. These lines. That's not really right. It should be over here at 2 pi, then over here. Okay. Not only that, then we're interested in where is it 0? Well, it's 0 where sinus is where our sine value is equal to 0. So at 0. Sorry, I did it wrong over here. So it's going to be 0 over there. So sorry. So it's going to be 0 where sine is 0, and then you're going to get an asymptote for a cosine is over thing. So it's not right what I drew here. I did it for the cotangents. So it's, let me redraw it. It's going to be here at pi over 2. Then let's draw pi, then 3 pi over 2, then 2 pi. Okay, like this. Let's draw some asymptotes. So we're going to get an asymptote at pi over 2, because that's where cosine is 0, and at 3 pi over 2. And then at minus pi over 2, we're going to get another asymptote. And between that, it moves from negative infinity, making sure that we reach 0 where we need to reach 0, and then it's going to go up to positive infinity again, and it's going to keep performing this kind of behavior forever. Okay, so that for our tangents. Now then, let's move to question number E, where our function is equal to minus 3 cosine of x. Our period, easy to be defined, 2 pi over b. b is 1, so our period is just 2 pi. Our amplitude in this case, which is going to be our absolute value of our a value, is going to be 3. What does this mean? Let's draw this once. It's going to be negative 3 cosine of x. Basically, now you see that the circle has increased and you move between 3 and negative 3, right? So it's the same behavior and the same repeating pattern, but now it goes up and down much further. But it does not run around the circle faster because our period didn't change. So our only way, if you want to sketch this, basically we did already the base case scenario and we saw that it looks somewhat like this. You have some kind of repeating pattern that looks like this, right? Imagine that this is all the same height, or this is 1 and negative 1. You're now going to end up with exactly the same thing, but now you're going to be between 3 and negative 3, meaning it's going to look somewhat like this. It doesn't need to be perfect, just something like this, more or less. Okay, so that for question E. This is a quick sketch, this is our amplitude. Then let's do maybe one more. Let's do question G. I still have some room here, so let's do it over here. It says tangents 5x plus 1. So first let us identify our period. And our period is going to be pi over b, which is just going to be pi over 5. Meaning that we run around the circle 5 times as fast as before. Right? But there's something else that I haven't really talked about, is this plus 1. And then you ask yourself the question, what does that do? Well, think of the function transformations of last week. Here a plus 1 means that our roots that we had before are all going to shift to the left, right? And by how much are they going to shift? Well, our shift is going to be minus 1 over 5. Because where before it was 0, now it's going to be 0 at minus 1 over 5. Okay, so how can you keep track of this? Well, let's have a look at this. We can say tangents 5x plus 1, and these are why these transformations of functions are so useful to know, because you didn't have to do any calculations and you would immediately know, well, it's going to move that much to the left. So in this case, you say 5x plus 1 is equal to 0. Okay, meaning that now you have to write arctangents of 0 is equal to 5x plus 1. Okay, then let's have a look at our arctangents. And our arctangents of 0 is at 0 degrees. So we find that it's going to be at 0 plus k pi, because remember, every 180 degrees we're going to end up with the same thing again with a tangent. So k element of z, of our integers, is equal to 5x plus 1, or in other words, minus 1 plus k pi is equal to 5x, or x is equal to minus 1 over 5 plus k pi over 5. And here you can see your period, and here you can see your shift to the left, right? So you're gonna end up, instead of being over here, over here, over here, no, everything is gonna move minus 1 over 5. Okay, let's plot that quickly in Desmos. So, tangents of 5x. See, this already becomes much more busy, the screen, plus 1, like this. No, not degrees, like this. So you see over here where you're at 0, now we moved minus 0.2 or minus 1 over 5. And this is what it's going to look like. Okay, so that's for question 2. I strongly encourage you, so I recommend to make the following exercises at home. I recommend you to make question D, F, and H. Really try to think about these function manipulations and also try to think about your identities of trigonometric functions. Okay. Then let's move on to question number 3. And here what we're interested in is basically trying to solve things. But we've already done that a couple of times. So basically over here you're already solving these trigonometric equations. But now let's make some real exercises on them. So for the first one, we're interested in tangents x is equal to 1 over the square root of 3. Okay, let's have a look at our table. 1 over the square root of 3 over 3, it's going to be at pi over 6. So that means I'm going to write it full out. The arc tangents of square root 1 over square root of 3 is going to be equal to pi over 6 plus k pi. Because remember, every time it keeps coming back, the same thing, right? Over here, and so district 1 and 3 are going to have the same answer, and 2 and 4 are going to give you the same answer. So that's why this plus k pi. Okay, meaning that x is going to be pi over 6 plus k pi with k an element of our integers. Okay, so that for C. Then let's make F. And here we're interested in the sinus of x. When is that equal to -1? For this, let's have a look at our circle. So sinus, remember, it's our y-axis, means it's going to be equal to -1 over here, right? Is there another point? Because, well, up above, you will see in the theory overview that there is always going to be 2 answers. Well, the 2 answers over here actually overlap. So it's going to be at 3 pi over 2, or you could say sinus, I'll use some different notation, so you have seen that one, sinus to the minus first, minus 1, x is equal to 3 pi over 2 plus 2k pi. K an element of Z. Okay, so that for F. Then let's make G, because sometimes you have to apply some tricks. So here we get tangents squared of x is equal to 3. Okay, how would you solve that? Well, we don't know anything about squared of tangents, so maybe we can just get rid of it by applying a root, and you definitely can. So we take the root of both sides, and then you find plus minus the root, because you always get 2 possible answers when you bring a square root to the other side with you have power, so it's the same as x squared is equal to 3. It means that x is going to equal to plus minus the square root of 3. So in this case, it means that tangents x is equal to these 2 possible values, right? Okay, meaning that x is either equal to the arc tangents of square root of 3, or it's equal to the arc tangents of negative square root of 3. Okay, then let's have a look. So square root over 3, quickly found, it's pi over 3. We can already say it. This is pi over 3, remembering that it comes back every pi times plus k pi. Okay, now minus pi over 3. And here we have to be a little bit more creative. We have to think a little bit further. In this case, you say, well, minus pi over 3. Okay, very, very interesting, very nice. But what can we do with it? Well, what you say is, it means that either the cosine or sine, they need to be, well, still have the same proportion, but one needs to be positive and the other needs to be negative, right? Now, meaning that we're going to end up, well, in this case, where we have a tangent of this value, where it's going to be, and you can see tangent is equal to 1, but now we're interested in finding where basically we end up with the same proportion, so something that would have the same distance along the sine axis and the cosine axis, but one of them being negative. In that case, you could just say, well, in this case, let's consider our sine to be negative, and that means that we're on this side of the angle, meaning that we are at negative minus pi over 3. So minus pi over 3 plus k pi, right? If you want to draw that, well, try to make sense of it. In this case, you're interested in making, for example, your sine or cosine, you would end up with the same thing. This is what this k pi, it would just give you an answer in a different quadrant, but imagine we're interested in finding an answer in quadrant number 4, meaning that our cosine, well, needs to remain in here, but here we need to find a negative value that's going to be as far along as the other side, and then the only possible answer is at minus pi over 3. Okay, so that for question G. Then let's make question H, which is our first question as well on cotangents, and it's going to be the cotangents of x over 2 plus pi over 2 is equal to 1. So here we have to work around a little bit because, well, we're going to find x over 2 plus pi over 2, doing the inverse operation on the other side, meaning that we're going to do cotangents to the minus first, or the arc cotangents of 1. So the arc cotangents, where is it? It's going to be at pi over 4, right? Because pi over 4 gives us cotangents pi over 4, it's going to give us 1. So arc cotangents 1 needs to give us pi over 4. So it's going to be pi over 4 plus its period, which is k pi. And now we find x over 2 plus pi over 2 is equal to pi over 4 plus k pi. But we're interested in finding x, so now we just need to do some algebra. First we move pi over 2 to the other side, so we find minus pi over 2, minus pi over 4. Let me redraw this, minus pi over 4 plus k pi is equal to x over 2. Let's bring the 2 to the other side. We find x is equal to minus pi over 2 plus 2k pi. And don't forget that if you multiply this, also this part is going to be affected. Okay, so far for H. Then let's make one more question, and it's M. In this case, you say sinus squared of x plus 4 cosine x minus 4 is equal to 0. Okay, and you might think, well, something squared plus some kind of function, not squared, minus a constant, that looks very much like a polynomial. And yes, it is very much a polynomial. You could solve it as a polynomial, and you'll see we'll use the discriminant, but we're a bit stuck because if we want to do a substitution, right, remember we could say t is equal to x squared, but why wouldn't we be able to say t is equal to cosinus x? And that's exactly what we want to do. But the problem is, here we're dealing with a sinus. And for this, I want to bring back the rule I explained earlier. Sinus squared plus cosinus squared x is equal to 1. Or sinus squared, how can you write that with only cosines and some constants? It is 1 minus cosine squared. of x. So this is going to give you minus cosine squared x. I'll write the 1 here for now still. Plus 4 cosine x minus 4 is equal to 0. Simplifying this 1 and this negative 4, you'll just end up with minus 3. Okay, meaning now we can do our substitution. We can say, okay, minus t squared plus 4t minus 3 is the one we're interested in solving, and then we just have to substitute back at the end. Okay, cool, let's do that. This gives us a discriminant of 4 squared minus 12, so it will give us a discriminant of 4, or in other words, plus minus 2 minus 4 over negative 2. Giving you 2 possible answers, it's going to give you either 1 or 3. These are your 2 possible values for t that could give you an answer. Okay, but now we have to be careful because we need to remember that t is equal to a cosine value. And here we can say, well, 1 is equal to, let me do it the other way around, it makes more sense like that. Cosine of x, doing our substitution back, what would that mean for 1? Well, it means that x is equal to 0 plus 2k pi. Okay, great. Then we can solve our other one, and we can say cosine x is equal to 3. But there is a problem, because while looking at this circle, our standard cosine function, it could never go higher than 1, and it could never go lower than negative 1. So we can never actually reach this point 3 over there. If you draw it in decimals as well, you will see that this function moves up at the most all the way to 1, meaning that this point over here, this 3, is unattainable and so not a solution of our equation. So our only possible solutions that we can find is for this part over here, so x is 0 plus 2k pi. Okay, then of course I'm going to recommend some exercises for home. I picked them out carefully, so there's a bit of everything in there, so I would suggest that you make question D, J, and L. Okay, then question 4, it's a little bit of a recap of, well, basically what we're doing here by doing these arc functions and these inverse trigonometric functions. So question 4 is for home. Let me try that again. So recommended for home 4. I'm not going to run over this in class unless it's really necessary, but this is really, if you say, oh, it's still not very clear, I don't really understand, try to make this exercise as well. Okay, that being said, I'm going to make one more exercise within the trigonometry part, and we're going to make 5a together. And here you have to prove that some kind of relation is true. So 1 minus 2 sinus squared of alpha is equal to 2 cosinus squared alpha minus 1. Okay, this is not immediately obvious why this is true, so let's maybe put our unknowns on one side and our constants on the other. So basically we move this 1 over here, so we get minus 2, and here we get minus 2 sinus squared alpha minus 2 cosinus squared alpha. Okay, this already starts looking like something. Let's divide both sides by negative 2, so we end up with 1 is equal to, so I'm dividing by 2 on both sides. No, not by 2, by negative 2. We end up with sinus squared alpha plus cosinus squared alpha. And this, because of Pythagoras, needs to be true. So that expression that was there over there is true. Verify the same for B. Do that at home. Okay, this is basically the part on trigonometry. We will use this later as well for complex numbers. After this, we're going to have a look at the systems of equations. But for this, I'll see you in the next video. See you there.